Before I introduce tonight's speaker, I wanted to say a few words. So we don't have as many video games as last night here, but I think the food was definitely better. Nothing against Dave & Buster's. They have good food too. But I wanted to start up by thanking a few people. First, I wanted to thank our Soul Platinum sponsor, Toptica. I see Tom right there. Let's give Tom a round of applause and Toptica. Their contributions help sponsor this dinner, so thank you. I also wanted to thank the caterers, Tasteful Connection. Let's give them a round of applause. And I wanted to thank Robin Rose-Chandler. Robin, if you could stand up, let's thank her for organizing tonight. And she's organized pretty much everything in the workshop. If any of you have asked me some practical questions about the workshop, you've probably heard me say, I don't know, you have to ask Robin. So thank you, Robin. So you're sitting in a soundstage, a Hollywood-approved soundstage that's brand new and open for business to the movie industry. And it's part of something called Magic Spell Studios, which just opened up in October. It's a $30 million proposition that got funding from New York State, from industry, from the local municipality, and alumni, donors. And it's the culmination of a vision to bring together multidisciplinary studies in media, art, gaming, interactive games, and movies, film, animation, in a way that connects students and professors with industry. And that's part of RIT's hallmark. And it's something that I've been involved in, not in the movie industry, but in detectors, scientific detectors. It's one of the reasons why I came here. And it's one of the things that we're trying to do with quantum. So you're seeing the culmination of a vision in a particular field, but you're also here at the beginning of a vision for RIT in quantum, where we're going to bring together students, professors, research, technology, science, engineering, and industry. So I'm going to tell you a little story about how I met Ryne Raffaelle, our speaker, and I haven't talked to him about this. So this was maybe 13 years ago when I first came to RIT, and I was interviewing here. Previously, I was at the Space Telescope Science Institute, which is the organization that operates the Hubble Space Telescope, and will be operating the James Webb Space Telescope. And I was the detector scientist for the James Webb Space Telescope. I started working on that project in 1999, and at that time we told everyone it would launch in 2007. And I don't know if you know anything about JWST, it hasn't launched, okay? In the year 2000, we told everyone it would launch in 2008. In the year 2001, we told them it would launch in 2009. We figured if there was 7 years in the future, we'd have a fighting chance of being able to build it eventually. And I think the time to launch just crossed over, and I think it's supposed to launch in 2021. But I keep updating the slide in my class, in my lecture, year by year. And I had dinner with Charlie Bolden a few years ago, the head of NASA, and he asked me if the deployment procedure was going to work, because JWST is too big to fit in the fairing of a rocket. And so we have to crunch up the mirror, and then at the press of a button, it's going to expand out of its box on the far side of the moon, where it can't be fixed. But we won't have to fix it, right? That never happens. So I worked on the deployment procedure. So I was the detector scientist, and I was the wavefront sensing and control scientist to figure out how to deploy this thing so that the mirrors were phased within a few tens of nanometers. And so Charlie Bolden asked me, is it going to work? And this is a few years ago, so I'd already been at RIT. And I said, I'm not working on that program anymore. So that was it. So hopefully it will work. It won't end up at the bottom of the ocean. Hopefully it'll launch. So in 2006, I was interviewing here through a mid-career change. And I was also interviewing at a number of other universities. And I won't say names. One of them was in Palo Alto. Another one was in Ithaca, New York. Another one in Madison, Wisconsin. And another one in Philadelphia. It was one of the schools in those locations. And those are great schools, and they have a long tradition of being great. And I'm an astrophysicist by training. And I was also interviewing at RIT. And RIT was very different. And it's the reason why I chose to come here, because I explained the vision of what I wanted to do, just like I did at those other places. and the reception was different. The other places I was seen as a traditional astrophysicist, which is fine. But what I wanted to do was combine science and engineering and industry, and I wanted to be able to be a part of missions, research and development, and all aspects of practicality, even starting businesses and et cetera. And RIT welcomed that, so they wanted cross-disciplinary applied research. And that's another reason why we're interested in steering our efforts in quantum towards quantum technology development. So when I came here, I interviewed and I talked to Ryne, and I explained this vision. And when I say that RIT liked the idea and was very receptive and supportive, when I say RIT, I mean Ryne and several others. So he was very supportive because he said, that's what I'm doing. That's what I do every day. Every day I'm allowed to wake up and do anything I want in engineering and science and combine any other departments that I happen to want to combine. In my Center for Detectors, it's not in a department, it's a research center, and we've had over 100 students over the past 10 years from, I barely know, but sometimes people ask me and I have to look it up, from 12 departments and 5 different colleges. We've even had 4 MBAs do studies for us. And like I tell the students when I first hire them, check your major at the door. Your new major is solving problems. We solve problems. That's what you're learning to do. And if you know mechanical engineering, that's great. Here's a ZMAX key, and you're gonna be an optical engineer for a semester. Not because I wanna teach you optical engineering. It's because we have to solve that problem. And then most students at RIT are eager to be involved in something that has real world application and is involved in a real project. And so they like learning about all sorts of things, not just in their major. So that's the story of how I met Ryne. He was a lowly professor at that time, like I am now, but now he's the vice president for research at RIT, and let's welcome Ryne Raffaelle.
So I did warn Don. I said, you know, I do get to speak after you, right? And I too remember when Don came here to first interview, and I remember it very well. So we sit down, and Don said, well, you know, full disclosure, you know, I've already received several offers that are being considered at a number of other institutions, and he proceeded to name 4 or 5 of these institutions. And then Don says to me, so, you know, I've heard of these other places. Why would I want to come to RIT? So that's how we started. But what Don said is absolutely true. Like, I used to direct the Nanopower Research Lab, and one time I totaled up, we had like 27 different majors that had worked in the lab. And this is that kind of place. So, as you might, for those of you who remember the Johnny Carson, The Tonight Show, I'm Tony Randall, okay? We had lined up a Nobel laureate to come here and give our keynote address, and unfortunately, at the last minute, that didn't work out, and so I was pressed into service. The good news is I am a physicist, and know something about what you all are doing. So, you know, I thought, all right, I got to give a talk, so begin with a joke. That helps. And you know, I thought about, okay, what am I going to talk about? Well, you know, what does a physicist talk about when they're not talking about physics? I don't know. So guess what? I'm going to talk about physics. But it's not what you expect. So let's talk about quantum 1.0, the origin story. 'Twas the late 1800s. The Brooklyn Bridge just opened. Just invention of the telephone, radio, the first modern Olympic Games. And the Statue of Liberty just arrived in New York Harbor. But you want me to tell you about the physics. Okay. Well, to understand the physics, we have to go back to 5th century BC and to the ancient Greeks. I just scared the shit out of you, didn't I? It's not that kind of a talk. Just relax. Come on. So we have Leucippus and we have Democritus. So question, which one was the professor and which one was the student? I don't even have to tell you. But as many of you may know, here's a famous quote from Democritus: "Nothing exists except atoms and empty space. Everything else is opinion." Love that quote. And of course, so they're credited with this atomistic theory. Everything's made up of atoms. And some guy, John Dalton, he used that to great effect, and periodic table and all the rest, but that's chemistry and we don't care. The thing that I find interesting, though, you notice we got these two pictures of a couple of ancient Greek guys, and they're in color. And then we got John Dalton, some Brit from the 1800s, and then it's black and white. Can you explain this? I don't know. Oh yeah, I forgot. He was colorblind. Actually, John Dalton wrote the first paper, scientific paper on colorblindness. He and his brother, also a famous chemist, they were both colorblind. This is what the talk's going to be like, so you can relax. Well, of course, in 1687, we got Principia, and that kind of dominated science for the next 200 years. We had a clue. We could figure things out. And really the big contribution was this idea of determinism. I've got the laws. You give me the input variables. I can predict what's going to happen. So let's see. You're coming to Rochester for a workshop in the middle of January. Yeah. I was pretty sure it was going to be cold, probably going to snow, have some travel problems. There's some other things going on. I'm pretty sure I could have predicted those too. Some of our government friends aren't with us tonight. That's unfortunate. Okay, back to the late 1800s. Okay. As you all know, Newtonian physics was starting to fail us. We couldn't figure out this black body radiation thing, this photoelectric effect. What's up with this atomic spectra? So something had to change. Well, here we go. Our buddy Planck comes up with this idea of quanta. The year was 1900. Boy, he looks like a happy scientist, doesn't he? I had to scour the internet to find something where he looked that happy. I did manage to find the picture of Planck after he learned that he won the Nobel Prize. Of course, Einstein used this idea of quantum. He was able to describe this photoelectric effect, and here's what he looked like when he found out he won the Nobel Prize. But guess what? When he found out that he won the Nobel Prize for the photoelectric effect and not the general theory of relativity, Niels Bohr model of the atom, helped us figure out A spectra. Works pretty good for hydrogen. Close for some of the others, 1913. And of course, a lot of other folks kind of pitched in there, and they too all won Nobel Prizes. Oh, and our friend Niels Bohr also won the Order of the Elephant. He was from Denmark, and they have this Order of the Elephant. The only time that that's ever been given to somebody who wasn't royalty or head of state, to this day. That is the Order of the Elephant, by the way. Nobel Prize, Order of the Elephant. So we can explain this stuff now. Black body radiation, photoelectric effect, we can describe hydrogen pretty well. Heck, I can combine those two and I can tell you what the black body temperature of the sun is. We had Dirac, Heisenberg. We needed a little bit more physics in order to figure out, say, spectrum like that. Anybody know what that is? Okay, I'll give you a hint. That's me running the Iron Man. Yep. Okay, by 1910, we had quantum mechanics. World would never be the same again. Transistor radios, transistors, solid-state computers, photoelectric effects. There were some unfortunate things as well. All right. So that brings us to what I call Quantum 2.0. About 59 years later, what we now would look back on and call the nanotechnology revolution. And there's plenty of room at the bottom. So enter our friend Richard Feynman. He gives his talk at the local APS meeting out there at Caltech, 1959. And it was an invitation to enter a new field of physics. Of course, he also got the Nobel Prize, not for this. Something about relativistic form of Maxwell's equation describe quantum electrodynamics, okay? It's all the same. Get the Nobel Prize. Come up with quarks. He starts talking about an old friend of ours, Heikki Kammerling-Onnes, the father of low-temperature physics. He's like, man, wouldn't that be cool? Wouldn't that be cool to start a whole new field of physics? Man, that's something. And of course, Heikki won the Nobel Prize for the discovery of superconductivity. He was the first to liquefy helium. And of course, you know, if you liquefy helium, what's the first thing you're going to do? You're going to start sticking stuff in it, right? And you know, the first time you have some liquid nitrogen in the lab, you know, sure, start with a balloon, that's okay. A lot of other stuff. You probably heard the story about Los Alamos, you know, the guys that were digging the tunnels, and they had all a lot of liquid nitrogen around, and, you know, there was mice and rats everywhere, so they would catch them, and they would stick them in there, and they'd chuck them against the wall, and they would just burst into a million pieces. They thought that was really cool. Guess what happened in the summertime? After all that stuff, you know, say, melted. They say you can smell it to this day. Anyway, he coined the term enthalpy. He's making up words. Won the Nobel Prize. The Nobel Prize story is fantastic. I don't know if you've ever heard this one, but so he's up there at the University of Leiden, you know, Leyden jar, all of that, and they used to have these, really what were technicians. They called them the blue coats, right? These were students, but they weren't students who were getting PhDs. They were the students getting trained on how to make things, machinists and all this kind of stuff. And so he's got this blue coat working in the lab, and you know, they're measuring the electrical conductivity of materials as you cool them down. And so, you know, they're sticking the mercury samples down in here, and you know, he's taking the data and he takes it to their professor, and he's like, you know, unfortunately I got down to whatever, 3 Kelvin, and then, you know, the resistance went to 0, and the professor's like, you know, the leads must have popped off. You must not have done it right. You know, do it again. Poor student goes down there, puts it all back together, does it again, same thing happens. He does this over and over, and he goes to the professor, and he's like, I don't know. I mean, I took it apart. They're still in contact. And the professor's getting upset. You know, you're worthless. And the kid finally says, well, you know, is it possible that maybe this is what the material does? You cool it down that low, and the resistance goes to 0. I mean, isn't it possible? You know, and he thinks about that for a while. And, next thing you know, he writes it up, wins the Nobel Prize. Kid doesn't even get a footnote, not acknowledgement, nothing. There was a whole sort of movement to try to get the poor guy recognized. But anyway, it pays to be the professor. All you students remember that. Oh, he also coined the phrase, how low can you go? That's not true. That's not true. I did think it was kind of cool, though, with all this quantum computing stuff and the dilution refrigerators, and now it was kind of apropos. But I digress. Feynman says, hey, I kind of screwed that up. He said, wouldn't it be great to have this whole new field of physics, the physics of small dimensions, and he put out these $1,000 challenges. Could we write the entire volumes of the Encyclopedia Britannica on a head of a pen? And then he went on to kind of derive that this should be possible, right? And if we did it, how could we read it? And can we make a motor the size of 1/64 of an inch cube? Now, somebody cashed in the very next year on the motor, but they really cheated. I mean, they used a microscope and some jeweler's tools and some, real small watch parts, and very carefully put it together. And Feynman kind of had to cash out, but this isn't what he had in mind. But he went ahead, he gave them their $1,000 check. But then he famously kind of wrote a letter that was published and said, hey, since I gave this silly talk, I've gotten married, I bought a house, I had a kid, I got a mortgage. Physicists, take your time on the writing of the page of text, would you? Give me some time to make a little bit of money so I can actually pay it off. And then a lot of people, kept writing to him and, well, I did this, I did that. And he's like, you guys, you're not getting what I was talking about, right? They were missing it by orders of magnitude. But it was interesting in that talk, he alluded to a lot of things that, ended up coming true, nanoprint lithography, the whole field of nanobiophysics. He talked about quantum dots, artificial atoms, and even quantum computing. So I love this story. So there's this guy up here, graduate student, Newman, and his advisor, Pease, actually were able to use an electron beam and do some electron beam lithography and write the first page of A Tale of Two Cities on a 200 by 200 sheet of polymethyl methacrylate. And it was really great the way it happened, because they're building this electron beam and being able to control it very accurately on very small scales, getting all the lensing worked out. That's what they were working on. And they weren't working on trying to write a page of text on a small area. They were trying to control electron beams. They kind of stumbled onto this field of electron beam lithography. But what was great about the story is Pease, the advisor, was off at a conference. And Newman, the student, he reads that old Feynman lecture, There's Plenty Room at the Bottom. And he starts thinking about it, and he's like, what I got in the lab, I might be able to do this. So while the cat's away, the mice will play, advisor's gone, he goes in there and he starts playing. And didn't quite get it. Advisor comes back, says, what you been doing? Kid comes clean, says, I was trying to do this, and there was this famous thing. Advisor gets really excited. It's like, that is so cool. Forget about our funded research projects. We're going to do this. And so they knuckled down. They did this page of text. They said it really helped that, the first line, it was the best of times. It was the worst of times. Everybody immediately recognized it. So the kid writes a letter to Feynman and says, hey, this is 26 years later. Did anybody ever claim that prize? And Feynman, a couple days later, the phone rings. It's Feynman's secretary, says he wants to talk to you. Kid about passes out. He said he was so nervous. And Feynman answers his phone and says, so, Newman, what you guys up to up there? He ends up coming visiting the lab. They show him what they did, and he ends up writing him a real nice note and sends him the check for $1,000. So here's something that's probably a little bit more impactful. good old Binnig and Rohr, their discovery of the scanning tunneling microscope. So this was great. I got to meet Heinrich Rohr when I was a graduate student. He came by the lab. I told him what I was doing and everything. First thing he said was, "Oh, you need to build an STM." But we also talked about, their discovery. This was really cool. I mean, that IBM lab in Zurich there, Switzerland, just a year before they won for high TC superconductivity, then they won for this. And what's remarkable about both of them is, usually you do something, you publish it, it takes a decade or two for the community to kind of embrace it, reproduce it, believe it, and then eventually you're recognized with the prize before you die because you got to be alive to win. These guys, paper comes out next year. They're going to Stockholm. It's pretty cool. And in talking about the discovery, Rohr said that when they submitted their first paper, with their first images of graphite and whatnot, he's like, the reviewers trashed it. I mean, just trashed it. And he's like, that's when we knew we really had something, because they knew it was right. I mean, they had worked it out. They had, they knew it was real. And so rather than being crushed and disappointed, he knew that eventually science would catch up and they would be vindicated. And when they were, because nobody believed it was even possible, they were really going to be shaking up the world, and of course they did. And there you go. They got the Nobel Prize right away. So, right after, a year after STM, then we had AFM, and then this M and that M and MOUSE. There were umpteen flavors of different scanning atomic microscopies. When I was at NASA, we worked on STORM, scanning, tunneling, optical resonance microscopy. You had a cool name. Basically, we're doing STM and hitting it with a laser, right? I guess what happens when you hit a semiconductor with a laser above the band gap. Surprise. Anyway, STMs came out. There was commercial STMs, and you could not only image with them, you can write with them, and everybody remembers this famous picture from IBM written with individual, I think it was sodium atoms on gold. Is that right? I believe that's what it was. Then we had the discovery of Buckminster fullerene, a new allotrope of carbon. Are you kidding me? How did we never see it? The first caveman who made a fire produced some fullerenes. Oh, we just didn't know they were there. We never looked for them, right? And so good Harry Kroto and Richard Smalley discovered the fullerene. I got to meet both of these guys and actually spend time with both of them independently, never together. So Harry Kroto, Sir Harry, right? He ends up getting knighted and all of that. What you may not know about him was he was an artist. That was his true passion, and he was a great supporter of the arts. We have this really interesting art collective here in Rochester. What the heck's it called, Don? It's called Artisan Works. And it's where it's a banding together a bunch of artists, and some philanthropists give them some money, and they sit there and they work, and and they hold events there and whatnot. So I was able to host Sir Harry because he found out about this place, and he came there, and he was a blast. And when he talked about this discovery, he said it was to him much more about art than science. I mean, he's sitting there in his office with some balls and sticks trying to figure out how they can go together, and it wasn't very mathematical and not too much chemistry there. Richard Smalley, he's one of those Nobel laureates who, he won, and he really leveraged his fame at winning the Nobel Prize. because he started becoming one of the greatest advocates in the country, perhaps the world, for solar energy. Also a big believer in the hydrogen economy, so I got to interact with him at a number of conferences. And of course, they got the Nobel Prize. And one of the interesting things about Richard, and you know, if he were still with us, he would back me up, is that, yeah, the fullerene's cool, you know, it's kind of an, you know, interesting nano soccer ball, but by far the much more interesting material is the single-walled carbon nanotube. And in terms of practical applicability and engineering devices and what have you. And just one little shameless plug for RIT, we make some of the best single-walled carbon nanotubes on the planet. And I'm not just saying that. They got plenty of data to support that. We actually do it by laser vaporization, which is kind of neat. And you know, there's a picture of some of the nanotubes that we produced here. And I'll tell you, when you have really high purity, pristine carbon nanotubes, low defect density, real long lengths, debundled, all this kind of stuff, and you put them into devices, you know, there's a lot of ways. Any way that you can combust carbon, you can make nanotubes, right? But not all nanotubes are created equally. I'm here to tell you that. And there's really something special about having these really pure ones. And you know, I'm telling you, there's something inside of there. And if you look closely, you can actually see it. Here, let me change the contrast a little bit. And here's what's really freaky. You take any high-resolution image of a carbon nanotube sample, and you mirror it and put it side by side, you're going to see an alien. So there's something going on there. I don't know what it is. And who did that? That's not funny. Okay, in 2000, the U.S. launched, you know, really one of the largest scientific endeavors of my lifetime, the National Nanotechnology Initiative, NNI. Man, that sounds strangely familiar. In 2003, President Bush signed the Nanotechnology R&D Act, $3.7 billion. Man, NQI is only a third of that. You know, what Ed say yesterday, 1.27 billion. Man, he should have read Art of the Deal. So you may have heard, you know, the best thing about nanotechnology is that it will incentivize a whole new generation of physicists to want to learn quantum mechanics. Anybody remember who said that? See, for the life of me, I can't remember either. It could have been Smalley, it could have been Feynman, I don't know who it was. And unless anybody can tell me, I'm claiming it for my own. And we can use it now with NQI. Uh-oh. But of course, if you think you understand quantum mechanics, you don't understand quantum mechanics. That's usually attributed to Feynman. So if we look back over the last 50 years or so, this quantum 2.0 era, a lot has happened. The world, once again, will never be the same. We got new allotropes of carbon, new techniques for making nanomaterials are used in all kinds of different systems, new fields, nanomedicine, all these quantum engineered devices. You know, that old saying, smaller, cheaper, faster, better, took on a whole new meaning. So we got things like nanotubes, graphene, femtosecond. What are switches up to now? These are those little nanoscale islands of gold that they use for switching. It's unbelievable rates. You know, the integrated photonics. But unfortunately, we have gray goo. You know, these are those self-replicating nanobots. So unfortunately, life as we know it's going to end. So anything I say from here on out doesn't matter. That's good. So let's talk about the future. what comes next? Quantum 3.0. I'm sorry, we're out of time, and so we're going to have to go. Here's what I would say about, Quantum 3.0. If we look back on Quantum 1.0, those pioneers that really developed most of that, they weren't trying to change the history of mankind. They weren't trying to change the world. By and large, they're just trying to understand these weird semiconductor materials. That's what drove most of that theoretical quantum mechanical behavior back there. They weren't trying to solve the origins of the universe. They were trying to figure out, man, when I put this little wire down this little semiconductor, get all this nonlinear behavior, what's going on? But they changed the world. In 2.0, Feynman, he really was trying to start a new field of physics. He's like, hey, wouldn't it be cool? And so he's going to start this new field, and he was kind of successful. Took a while, but the reality is once we start playing at that real small scale, hey, quantum mechanics is inevitable. It kind of controls what happens. But when I look back at, the big discoveries and all of the technological transformation, it was more about, new forms of matter and ways of manipulating matter and imaging matter. And it was much more about textiles than really trying to exploit the, those weird, strange things that quantum mechanics predicts. Yeah, sure, we had tunneling, tunnel diodes and scanning tunneling microscopy and stuff, but I think if we look at 3.0, 3.0 has the advantage of knowing what happened with 1.0 and 2.0. So we understand, kind of how quantum mechanics works and what all those strange predictions are. We also understand from 2.0 how to use and manipulate matter. We have all these new tools for seeing and controlling these things. And I think that this next manifestation is going to sort of combine 1 and 2. It's going to allow us to start to exploit some of those quantum mechanical phenomena to do new, remarkable things. Quantum computers and networks and even a quantum cloud, better detectors, sensors, images, light source or clocks, all these things. We know the quantum mechanical principles that would make them happen. We now know how to control things and see what's going on in order to produce them. And so I think that's what's going to characterize this next one. The other thing I believe that is the people in this room, quite literally, are the pioneers of this next quantum revolution. And, dare I say it, changed the world. And I really, truly believe that. So with that, thank you all for being here and doing what you do. And, I'll leave you with the charge. Go off and change the world. Thank you.